All right, y'all. It's just about 8:05, so we're going to get started. First, I have a little story for you. My handwriting may not be the same. I kind of injured my pinky on my right hand, so bear with me. I can still write, but it's just not quite the same. So I might be a little bit slower on the draw, might be a little bit messier than normal. But let me know if you can't understand something and I'll try to clear it up. So last week, we started chapter 8. We did a bunch of calculations with the mole. We learned about Avogadro's number, molar mass, and we also talked about molar volume with gases and density. This week we're going to finish up chapter 8, and then we're going to do some exam review, and we'll see where we land. Are there any questions for me, logistical questions or anything like that before we get started? Otherwise, let me know that you're ready to go. Well, let's go. So, the part of chapter 8 that we didn't cover last week, it's kind of almost like its own chapter, a little mini chapter. It still has to do with moles and stuff like that, but the calculations are a bit different. So that's why I split it up. We're going to start off talking about percent composition. Percent composition just tells you the mass percent of each element. So if you had water, like I did in the video for YouTube, what percentage of water is hydrogen? What percentage of water is oxygen? That's the percent composition. So I'll do a sample problem for you, and then I'll let you try one. It's a pretty simple concept. For our example, we're going to calculate the percent composition of methanol. What that means is that we want to know the percent carbon, the percent hydrogen, and the percent oxygen in this molecule. Whenever you're doing percent composition, you're going to have the mass in grams of your given element over the molar mass of the compound. And that will be multiplied by 100%. And you do that for each element. So for methanol, we've only got one carbon, we've got 4 hydrogens, and 1 oxygen. And of course, I wrote that one in the reverse of everything else. Let's figure out our molar mass. So as a quick review from last week, I want you to calculate the molar mass of methanol and put that in the chat. Remember to let me know if you're stuck. So if you don't remember what molar mass is, you can let me know and I can help you out. Yeah, it should be somewhere in the ballpark of 32. I'll write out how I got that. You have to look at the periodic table and figure out the carbon, the hydrogen, and the oxygen. And you add those together, remembering to take into account the fact that you've got 4 hydrogens in methanol. Now that we've got the molar mass, we can go ahead and figure out the percent carbon, hydrogen, and oxygen in methanol. For the percent carbon, we've only got the 1 carbon atom, so we're going to put 12.01 grams because there's 1 mole of carbon in this compound. And you're going to put that over the molar mass, which we just calculated. You multiply that by 100%, and that is your percent carbon. So you should get something in the ballpark of 37.5%. For the hydrogen, remember you've got 4 hydrogens, so that's 4 times the 1.008, and you place that over your molar mass times 100%. That should give you about 12.6%. Why don't you try the oxygen and let me know what you get? It's not grams, it's percent. We'll call that about 50%. When you total those up, you should get about 100%. It may be like 100.2 or something like that. That's fine. With rounding, it may not be exactly 100%, but it shouldn't be 103% or 105%. Okay. Does everybody understand that concept of percent composition? Are there any questions on this slide? So we calculated the molar mass of the compound, which is methanol in this case. So you find carbon, hydrogen, and oxygen on the periodic table, and then you add all that stuff up together and get the molar mass. Any other questions? All right. I want you guys to do this one. I'll give you 5 minutes, and I'll write up here so that you remember. You want the mass of the element. So, for example, if you're doing carbon, you would want the mass of carbon times 9, right? Over the molar mass of the compound multiplied by 100%. I'll give you 5 minutes to calculate the percent composition of aspirin. How are we doing? Do we need more time? Okay, I'll give you another minute or so. I'm going to get started with setting it up. Don't worry about putting your answers in the chat. We'll just check in after I put it all up here and see how everybody did. The first thing you need to do is calculate the molar mass, which I abbreviate MM, of aspirin. We've got 9 carbons, 8 hydrogens, and we've got 4 oxygens. So you should have something in the ballpark of 180 grams per mole for your molar mass. When you set up all of your percentages, it should look a little something like this. So you should have about 60% for your carbon, somewhere in the ballpark of 4.5% for hydrogen, and somewhere around 36% for oxygen. I'm not going to be too big on sig figs here. How did we do on that one? Do we have any questions? Alrighty. So that's percent composition. Keep that in the back of your mind. We're going to use it again. Now we'll talk about empirical formulas. An empirical formula is the simplest whole number ratio of the ions in a formula unit or the atoms of each element in a molecule. So if we're looking at benzene, that's C6H6. That's the molecule. That's the molecular formula. The simplest whole number ratio is CH. So 6 to 6, that's 1 to 1. Remember, there's the implied 1 here. If your molecular formula is C8H18, the simplest whole number ratio would be C4H9. So you're just reducing the subscripts down as far as you can. And you can have a molecular formula that is a multiple of that. We'll talk about molecular formulas in a minute. The reason we care about empirical formulas is because we can calculate what an empirical formula is for a compound just based on how the compound was put together. So I'll show you what I mean in this example. Let's say that we've got a sample of chromium that was heated with excess sulfur to give a chromium sulfide compound. What is the empirical formula? We can't just assume that it's going to be one atom of chromium and one atom of sulfur. We have to figure it out. What we're going to do here is figure out the number of moles of chromium and the number of moles of sulfur in this compound. And we'll compare them and figure out a ratio. To figure out the moles, we have to know how many grams of each. We're already given, for the chromium, that we've got 1.162 grams of chromium. That's what was heated with the sulfur. But we've got this 1.878 grams of chromium sulfide. That doesn't tell us how much sulfur we have. But if we subtract the grams of chromium from the grams of this chromium sulfide that we have, we can figure out how much sulfur. So tell me how we are so far. Is everybody still with me? I said we have to figure out how many moles of each of these things we have. So we got to start with the grams, all right? This part is one of the most important parts, so don't forget that. Now that we've figured out how much sulfur we added to the chromium, we can go ahead and figure out how many moles we have. How do we go from the mass of chromium to the number of moles of chromium? We've got to use that molar mass. That's right. So you'd look on the periodic table. You'd figure out how many moles you have. We do the same exact thing for the sulfur. So we've got about 0.022 moles of both the chromium and the sulfur. That means that we've got a 1-to-1 ratio. So our empirical formula is going to be CRS. Now we don't know what the actual molecular formula is yet because we don't know the molar mass of this compound. But we know the empirical formula is CRS. Does everybody understand that part? How we calculated the moles, and then we said, okay, well, they're about the same. They're 1 to 1, which means that our empirical formula is 1 to 1. I want you guys to try a problem on your own. So I'll give you 5 minutes. It's the same type of problem. It even uses sulfur. It's just a different metal. You'll use the same process and figure out the empirical formula. If you get stuck, that's okay. When I check in with you in about 5 minutes, let me know that you're stuck. How are we doing with this one? This one's a little bit tougher. I'll wait another minute and then I'll start going over it. Yeah, that's totally fine if you're stuck. This one is a little bit harder. I'll get started setting up the problem. So we've got a sample of cobalt that's heated with excess sulfur to give a mass of cobalt sulfide, and we're asked for the empirical formula. We know how much cobalt, we know how much cobalt sulfide, but we don't know how much sulfur was incorporated. So the first thing you have to do is figure out how much sulfur was added to the cobalt. So this is the cobalt sulfide that we don't know what its empirical formula is. So that's what the X and Y are for. We don't know what those numbers are. And we take that mass and subtract what we know about the cobalt to get the amount of sulfur. Then we can take those and figure out how many moles of each using the molar mass. Are we good up to there? Were we able to, if you were stuck, did you figure out the number of moles of each? Okay. This is where it gets a little bit sticky, right? So before we had the same number of moles of each, so it was easy to figure out the ratio. It was 1 to 1. This time, we've got more sulfur than we do cobalt. But how do we find a ratio? You just divide, right? So if I've got that much sulfur and that much cobalt, when I do the division, I get about 1.5. So that means that I've got 1.5 moles of sulfur for every 1 mole of cobalt. 1.5 isn't a whole number, but if we multiply it by 2, then we get 3 moles of sulfur for every 2 moles of cobalt. That's our empirical formula. So did that help the folks that got stuck? Because I'm going to guess that this was the sticking point. You got the moles and then you said, okay, wait, so what do we do with this? So whenever you do not have an equal number of moles, you still figure out the ratio. You take the one that's bigger and divide by the one that's smaller. If you don't get a whole number, like in this case, then you just multiply by a factor that will give you a whole number. Go for it. So, so the ratio comes from, we figured out our number of moles of each, the cobalt and the sulfur. And then you divide those two to figure out how they're related. So when I did the division, I got 1.5. What that means is for every 1.5 moles of sulfur, I have 1 mole of cobalt. So you have to understand what that ratio is. Well, we can rewrite that 1.5 as is 1.5 over 1. So it would be moles of sulfur over moles of cobalt. But since we need a whole number ratio for an empirical formula, you have to multiply by 2 to get rid of the 1.5. Sounds like it still needs to process a little bit. So think on it and then ask me another question. Are there other questions about this? Because it gets a little bit more complicated when the ratio isn't just 1 to 1. So I wanted to give you an example of that because you'll probably see something like that on your Mastering Chemistry homework. So if you still have questions on this, but you just don't know what it is yet, that's fine. You can ask me we're going to take a break in between finishing up Chapter 8 and starting the exam review. So that would be a good time to ask questions that you didn't quite know you had before. But you can also always do office hours or send me a message through course messages on Blackboard. So we'll move on, but if you still have questions about this one, we can revisit it. So we figured out the empirical formula just by having the number of grams of a starting material and how many grams of product we made. That's one way to figure out empirical formulas. The other way is by using the percent composition. I'll do an example for you. This is the example that I did in the YouTube video. And it's a simple example, which is why I like it. So we have acetylene, which is a gas, and you can actually use it. So plumbers use it sometimes for doing soldering of like copper plumbing. So it's dangerous stuff. You don't want to play with it, okay? Acetylene is 92.2% carbon and 7.83% hydrogen, What is the empirical formula? Doesn't look like we have much to go on, but we do. These percentages add up to 100%. If we assume that we have 100 grams of acetylene, then that means that we would have 92.2 grams of carbon and 7.83 grams of hydrogen. That's how percents work. So if we have 100 grams of acetylene, we know how much of each element we have. That's the assumption you have to make when you calculate the empirical formula from the percent composition. You assume that you have 100 grams of your substance. From there, it's the same as before. You take the number of grams of each element and you figure out how many moles. So when you do that, you get about the same. So 7.68 and 7.77, that's pretty much 1-to-1. So your empirical formula is going to be CH. The only thing that was different about this problem is we had to make an assumption in order to have some masses to calculate the number of moles. So does this part make sense, where we assume that we have 100 grams? Okay. After that, it's literally the same thing. So how about y'all try this one? The percent composition of bismuth oxide is 89.7% bismuth and 10.3% oxygen. What is the empirical formula? I'll give you 5 minutes. How are we doing so far? Do we need some help or are we stuck? Or do we need more time or are we stuck? Okay. So this one is similar to the other one that we just did. We're going to make our assumption that we have 100 grams of our substance. So that means we've got 89.7 grams of bismuth and 10.3 grams of oxygen. We can calculate the moles of both of those. So I'm going to guess that everybody was able to do that part. But then you said, oh, they're not the same. Now what do I do? You're going to take the bigger one, which is the 0.644 moles of oxygen, divided by the smaller one. When you do that, you get 1.5. That's what your calculator says. But remember, what that's really saying is you have 1.5 moles of oxygen for every 1 mole of bismuth. Now, we can't put that as an empirical formula because it's not a whole number. But if we multiply by 2, then we get this. So don't forget about dividing. You take the bigger one divided by the smaller one, and that will tell you your ratio. Sometimes it'll be 2 to 1. Sometimes it'll be 1.5. But you have to remember what that ratio means. And this is the key. Write the ratio as a fraction, and that'll tell you what you need to know. Questions? I've got one more for you. I want you to try this one. This is one of those things that you just have to practice. We'll do this, and then we'll move on to molecular formulas, and then we'll take a break. So try this one. I'll give you 5 minutes, and we'll move on. Alrighty. I'm going to get started on this one because I know this one is a little bit tougher than the last one. This time we've got 4 different elements, and we don't have just a 1-to-1 ratio for all of them. So I wanted to give you this example so you're not stuck on your homework. We make our assumption that we've got 100 grams. That way we can figure out the number of moles. And I know y'all don't really have a problem with this part. It's the part that comes after. I'm sure as you were doing this, you were like, oh, great. Everything is going to be the same. It's going to be an easy one. And then it wasn't. We were good until we got to the oxygen. So is everybody okay with getting up to the number of moles of everything? Okay. So from what it looks like, the carbon, the hydrogen, and the nitrogen, they're all, whatever the empirical formula is, they're all going to have the same subscript. But it's this oxygen that's throwing a wrench in the whole daggone thing. What we have to do here is we're still taking the smallest number, and then we're going to take each one of these, the carbon, hydrogen, and nitrogen, and do that same division. When you do that division, you get 2.5. Your calculator is going to tell you 2.5. But you have to remember that that means 2.5 moles of carbon and 1 mole of oxygen. We can't do anything with that yet because it's not a whole number. But if you multiply by 2, then you get 5 to 1. The hydrogen and the nitrogen are the same as the carbon. So I'm not going to go through and write all those out. But if all of these numbers were different and oxygen was the smallest one, you would take the hydrogen, the number of moles of hydrogen, divide by the number of moles of oxygen, and do the same exact thing. It just so happens that if you do that for these, you get the same thing. So this is your empirical formula. How do we feel about that? Questions, or do we just need to practice? Okay. So you will see this in your homework. I wanted to try to give you kind of the run of the gamut there in terms of difficulty so that you could have examples to pull from. We've been focusing on empirical formula. Now we need to move it to molecular formula. The molecular formula is the actual formula of the compound. So we talked about CH is an empirical formula. And if you have a multiple of that, then you make a molecular formula. So C2H2 or C6H6. Those are molecular formulas. You can figure out what the molecular formula is if you have the molar mass of your compound and you know the empirical formula. So for acetylene, we did a problem with acetylene. Its empirical formula is CH. Acetylene has a molar mass of 26 grams per mole. Find the molecular formula. The first step is to calculate the molar mass of your empirical formula. Yes, I'm absolutely going to post this. So I will take the extra few minutes that it takes to I audit the video, make sure there's no weirdness and all that. And then I post it to YouTube. And then YouTube, once it's uploaded, it has to process so that the standard definition, high definition versions are available. And once that's done, then the video is actually available for view. So I will do that, and then I'll post the link. But the video may not be available right away, just because it may still be processing. So don't worry. The YouTube video for like the whole entire chapter, chapter 8, is up. And then this video has more examples of the empirical formula and the molecular formula that are not in the other video. So there is a benefit to coming to class. Look good on y'all. But I will absolutely post it so that you can see it and go through it and let it kind of marinate and get with you. So we're going from empirical formula and molar mass of a compound to find the molecular formula. The first thing you have to do is calculate the molar mass of the empirical formula. Our empirical formula is CH. Which is pretty easy. The carbon, we've been doing it for a while. So there's our carbon, there's our hydrogen. That's our molecular or our molar mass of the empirical formula. The next thing you do is calculate N. N is the multiple of the empirical formula. So this is how many times the empirical formula. And I'll show you what that means. We have a molar mass of 26 grams per mole. The empirical formula has a molar mass of 13.018 grams per mole, which is about 13. You take the molar mass of the molecular formula and divide that by the molar mass of your empirical formula. And that gives you N. Here we're saying 26 divided by 13 equals 2. So we take our empirical formula and multiply it by 2. This is our molecular formula. Do you see what I mean by how many times the empirical formula? You should get a whole number here. So if it's like 2.99, that's 3. But that's how you calculate the molecular formula from the empirical formula. Questions about that? Which I know you may not know what your questions are right away. You just need to practice it and watch it. But if there's anything pressing now, you can let me know. Otherwise, I have an example for you to try. Then I want you to try this example. We've got we're trying to find the molecular formula of lysine. Lysine is an amino acid. And the empirical formula is given along with the approximate molar mass of lysine. Take those two pieces of information and figure out what the molecular formula of lysine is. I'll give you 5 minutes. Do we need more time, or are we ready to go over this problem? All right. So we're looking for the molecular formula of lysine. We have the empirical formula, and we know the molar mass of lysine. The first step, we got to calculate the molar mass of the empirical formula. When you do that, you get 73.093 grams per mole, which is about 73. Then you have to calculate N. And that's the molar mass of the molecular formula divided by the molar mass of the empirical formula. Our molecular formula has a molar mass of 146 grams per mole, and we just calculated 73 grams per mole for our empirical formula. That should give you 2. So that means 2 times the empirical formula. Just like in math, you're going to multiply all those subscripts by 2. That is your molecular formula. How do we do on that? Go for it. Yes. Yes, so this is different from figuring out the ratio like we were doing before. This 2 is our N, where we just say, okay, now we know the molecular or the empirical formula, everything we have we multiply by 2. With the other one, it was a ratio, and that's a little different. Yeah, and we're going to combine the 2. So hold on to your hat. Okay, now we're going to string together all the things that we've just been doing. We started with percent composition, then we talked about empirical formulas and molecular formulas. Now we're going to go from a percent composition or a mass composition to a molecular formula. I'll show you how to do it. This is the same example I did in the YouTube video, but then I have some others for us to work out together. I just want to show you the process. Once you get the process down, it won't be that bad. So we have an insecticide that causes dizziness in humans. And all that we have is the percent composition, which has got carbon, hydrogen, and chlorine, and the approximate molar mass. The first step is going to be figuring out the empirical formula. And we do that using the percent composition. We make our same assumption, assuming that we have 100 grams of our compound. That means all of these percentages can turn to grams. Once we figure out all of our moles, we can figure out the ratio. They're all about 2. So the ratio of carbon to hydrogen to chlorine is 1 to 1 to 1. So our empirical formula is CHCl. That was step 1. Step 2, we're going to do exactly like we did before, is to use our empirical formula and calculate its molar mass. Take the molar mass of our compound, figure out N. Our empirical formula is CHCl. That's our molar mass for the empirical formula. Cannot stress that enough. You don't want to get your numbers confused. To calculate N, we take the molar mass of the actual compound and we divide by the molar mass of the empirical formula. When you get that, it's 5.98. That's about 6, okay? So our N is 6. That means we're going to take 6 and multiply by our empirical formula. And that is our molecular formula. So we just put those two pieces together. Questions about that? Because you know I'm going to have you do one. Then I want y'all to try this one. You need to figure out the molecular formula for lactic acid. And you've got the molar mass and the percent composition. I'll give you 5 minutes and then I'll check back in. Yep, I was just gonna get started. So if you would like to put your answer in the chat, you can. Or you can wait until the end for the reveal. And if you didn't get to an answer, that's okay. You can just walk along with me. Yes, that's the answer. Not gonna make you wait. You got it right. So the first step is figuring out the empirical formula. We assume 100 grams of lactic acid. That way we can take all those percentages and make them grams and figure out moles. Okay, we've got all of our moles. They're not all the same, so we have to figure out the ratio of the carbon to the hydrogen to the oxygen. You're going to take the biggest one and divide by the smallest one, which the carbon and the oxygen are the same. Exactly, Kierman, it's 2. That means that we have 2 moles of hydrogen for every 1 mole of carbon. So what that looks like is if you have 1 carbon, then you've got 2 hydrogens. The oxygen is the same, but I'll write it out anyway, just for clarity's sake. Oops. So that would be our empirical formula. That's only the first part. Now we have to figure out the molecular formula by calculating N. Start by figuring out the molar mass of your empirical formula. I'm not going to write out, all the addition here. I think we can all calculate molar mass. You should get something in the ballpark of 30 grams per mole. Can't stress enough. That's the empirical formula. Now we take the molar mass of the molecular formula that we don't know yet and divide it by the molar mass of the empirical formula. And you get 3. That means that we take our empirical formula and multiply it by 3. And that's the molecular formula. You may not have questions now, but as you go back through, as you revisit how we did these problems, you might have questions. So you can send me a message using course messages, or you can come to office hours on Wednesday, or you can do both. Are there any pressing questions now? You can ask them, or else we'll take a 5-minute break. So let me know if you're ready for break or if you have a question. All right. Then we'll break for 5 minutes till 9:50. Then when we come back, we'll start some exam review. See you in 5. Alrighty, it's 9:50. We're going to switch gears and do a little bit of exam review. So remember, your exam is coming up next week. It's going to be on chapters 7 and 8. So I wanted to start exam review this week, and then whatever few questions we don't finish, we can do those next week. But we're going to need all the time possible to go over chapter 9. So that's why I'm starting exam review this week. So we're going to dig a little bit backwards into chapter 8 and start doing those mole calculations. How many molecules of hydrogen gas are in 22.4 liters of hydrogen gas at STP? I'll give you a couple of minutes and then we'll go over it. If you have an answer, you can put it in the chat. Otherwise, I'll show you how to do it. We're looking for how many molecules. So I'll show you the long way, and then I'll show you the short way for this particular question. We've got 22.4 liters of hydrogen gas. And we are trying to go from a volume to molecules. So that means that our first trip is going to be from volume to moles. And then the second part of the trip is going to be moles to molecules. For the first part, we're going to use molar volume. And molar volume says that we've got 1 mole of gas in a volume of 22.4 liters. The next part, we're going from moles to molecules. We're going to use Avogadro's number there. You don't even really have to do the math there because everything cancels out. So you should have 6.02 times 10 to the 23rd molecules. Now you can go through all this math and that's great. But if you recognize that 1 mole equals 22.4 liters, that's the definition of molar volume, and that 1 mole is also equal to 6.02 times 10 to the 23rd molecules, then you're done. So knowing the definitions of these things helps. Any questions on that? Let's move on to the next one. Which of the following is evidence of a chemical change? And I want you to tell me all of the ones that apply. So read through A, B, C, and D, and in the chat, tell me which ones are chemical changes. So you can have multiple answers, you can have one answer. And remember, we want all of the ones that are chemical change. So it could be one, it could be multiple. Anybody else want to cast their vote? A, B, C, D. All of them? Just a couple? So the only one that is not a chemical change is C. All the other ones are. So the Alka-Seltzer tablet, when it fizzes in water, that's producing a gas. So fizzing and bubbling, that's evidence of production of a gas, which means you're watching a chemical change. Heating iron and air produces a dark red solid. We're making something new. So we've got iron, we've got air, which has all different types of gases mixed into it, right? And we're making a dark red solid. So that's definitely evidence of a chemical change. We're seeing a color change here. And then mixing two clear aqueous solutions produces a blue color. Again, that's another color change. So it's A, B, and D. Is everybody clear on that? Now I want you to classify and balance the following equation. And might I say, when you're doing your chapter check-ins, make sure that you read the whole question and answer all of the question. So that was a big problem with chapter 6, where you didn't classify and write the name of the formula or, the chemical formula. Make sure that you classify the reaction and then balance the equation. There's two parts. If you only do one part, you only get points for the one part. So make sure you read, and when you check over your work, which you should do, make sure that you answered all parts of the question. I'll give you a couple of minutes. Well, I know some people are fast, but I'll give another couple of minutes for y'all to breathe it in and come up with an answer. So I know we already have one answer. Anybody else want to take a stab at it? Maybe tell me what kind of reaction this is, even if you haven't finished balancing it. Okay. So I'm going to agree with that. This is a double replacement. We're mixing two aqueous solutions, and we're forming a solid plus a different aqueous solution. For balancing, for those who might be stuck or maybe just forgot, I'll show how it works. We have to tally up the elements or polyatomic ions on both sides. We see NO3, which is nitrate, on both sides, so we can keep it together. We don't see any nitrogen or oxygen outside of that. So we can count. We've got 2 mercuries, 2 nitrates, 1 sodium, 1 bromine. That's all on the reactant side. On the product side, we've got 2 mercuries, 2 bromines, 1 sodium, and 1 nitrate. So we're not balanced. We've got to balance the nitrates and the bromine atoms. And as we do that, we may need to balance some other things. Let's start with the nitrates. You find the lowest common denominator between these two, which is 2, and then you multiply as needed. So on the product side, we're going to find the compound that has nitrate and place a 2 in front. If you feel comfortable with it, you can just keep going without making another chart. I'm going to show you the make another chart way just because it's the best guarantee that you'll get it right. So we haven't changed anything on the reactant side. We can just copy that over. But we did change some things on the product side. We've still got the same number of mercury and bromine atoms. But now we've got 2 of the sodium atoms and 2 nitrates. So we're balanced with the mercury. We're balanced with the nitrates. But now we have an imbalance in the sodium, and we still haven't fixed the bromine. They're in the same complex, or compound, on the reactant side. So whatever we do to one, we're going to do to the other. The lowest common denominator is 2. So we're going to put a 2 in front of the sodium bromide. Then we take a final tally. We should be balanced after this. And if we're not, then we need to recheck some things. So we've got our 2 for the mercury and the nitrate. We haven't changed that. But we placed a 2 in front of the sodium bromide. So now we've got 2 each of the sodium and bromine atoms. We didn't touch the product side at all. So that should all be the same as the table before. Now we're balanced. If we were to list all of the coefficients from the reactant side to the product side, remembering that if there's no coefficient, it's a 1. It would be 1, 2, 1, 2. So that's some chapter 7 for you. How'd that feel? I know a couple of y'all got it. Yeah, with balancing equations, you just have to practice. I posted practice for chapter 7 along with an answer key. So you can definitely have more practice with balancing equations, more than you ever thought you'd want. And let's move on. Now we're back to chapter 8 land. We did this type of a question last week. Calculate the mass of a single molecule of carbon dioxide. Report your answer with 3 significant figures. So I will give you about 2 minutes and then I'll check in. Okay. I promised you this would be one of the questions on your exam. You're going to see something exactly like this. Maybe it's not carbon dioxide, but it will be a question like this. Watch carefully. We need to calculate the mass of a single molecule. This isn't a molar mass question. This is a molecules to mass question. We have one molecule and we're trying to figure out its mass. You have to go from molecules to moles and moles to mass. You calculate the molar mass, which most of you did, and that is 44 or so. But you have to use that in your calculation. You have to convert one molecule into moles. Then you use the molar mass to figure out the number of grams. So don't forget. For some reason, that question always tricks students every year. Don't be tricked. The mass of a single molecule, if I asked for the mass of 1.8 times 10 to the 23rd molecules, you would do it this way. It's the same thing for one molecule. Is that clear? So this is not a trick question. When you see one on the exam just like it, do not just put the molar mass. You should get a small answer because it's only one molecule or one atom. We'll do one more and then I think we'll call it. So how many atoms are in 5.78 grams of iron? I'll check in a couple of minutes and see how you did. You can go ahead and keep working, but I'll start writing up the answer here. Identifying the problem, we've got a mass, that's what we're given, and the question is asking how many atoms. We can't just jump straight from mass to atoms. We've got to go through moles. So we'll go mass to moles using the molar mass, and then moles to atoms using Avogadro's number. The molar mass of iron you just take from the periodic table. Your textbook has 2 decimal places. The periodic table that I gave you has 3. It's not going to make a big difference in your answer. So that's the molar mass part. And then we have Avogadro's number. When you do that math, you should be left with atoms yeah. 6.23, 6.22, they're both good. So we should have 3 sig figs here because the mass was given with 3 sig figs. And when you're doing this, don't forget to put your units. So in this case, it's atoms. Don't just give me the number, because you lose half point. So this is just some review from what we did last week, and then chapter 7, which is the week before that. Questions. Make sure you start studying. Do some practice problems. So I'm going to save this one for next week. This is a solubility one. And then we have another one on gas density. So you'll see those next week as part of exam 3 review. So I won't post them as part of today's lecture. I'll take those slides out. Here's your reminders for this week. You've got Chapter 8 Mastering Chemistry assignments due on October 25th. That's Sunday. So hopefully you were able to get started. There are some issues with Mastering Chemistry. The homework and the quiz should be up and available by now. If you don't see it, let me know. There have been a couple of issues with Mastering Chemistry, and I believe that they're going to be doing maintenance on Mastering Chemistry this weekend. So don't leave it all for Sunday, because you may not be able to get to Mastering Chemistry on Sunday. That's word to the wise. There's going to be a maintenance window. If you haven't gotten an email about it, you should be getting an email. But they're going to be doing maintenance on Mastering Chemistry and all the mastering stuff, my lab. So if you're in a math class, all that stuff is going to be unavailable for some time over the weekend. So plan to get things done by the end of Friday. You have exam 4 next week. It'll be available October 28th through Friday, October 30th. And it covers chapters 7 and 8. So we'll finish up our exam review next week and start chapter 9. You'll have your exam. I'm not going to give you any additional, like you don't have to do a chapter check-in or anything like that. I think that's too much. The exam, studying, all that good stuff. So no chapter check-in next week either. If you have any questions for me, this would be a good time. Otherwise, you're free to go.